quantum computer is a hypothetical machine that would exploit the principles of quantum mechanics that govern the subatomic world in order to solve certain problems much faster than we know how to solve them with any computer today. Quantum mechanics has been, the basic framework for almost all of physics for nearly a century. What it says is that if you don't know, what state a system is in, like you don't know if an electron is in its ground state, its lowest energy, or in the next higher energy. Well, the issue is in quantum mechanics, the different places where the particle could be, or the different paths that it could take to reach a certain final position, can all, as we say, interfere with each other. And if this happens, then these different paths can cancel each other out. And so then, if some are positive, others are negative, then maybe you won't find the particle at that final place at all. A classical computer, of course, is based on bits, which are a bunch of elements that can be either definitely 0 or definitely 1. Now, a quantum computer is based on quantum bits or qubits, which can be, as we say, in a quantum superposition of the 0 and 1 states. Okay, now the way that most popular articles like to put it is that it can be 0 and 1 at the same time. And the problem is that, at some point you've got to measure the computer to figure out, to read out an answer. Which answer you see will be determined by these amplitudes. What an amplitude is it's like a square root of a probability. Now, the key point is that the same number can have more than one square root. For example, 2 and minus 2 are both square roots of 4, right? So corresponding to that, you can have either a positive or a negative amplitude. Okay, now what a quantum computer would be is a computer that would exploit this phenomenon of interference between positive and negative amplitudes on a massive scale. Okay, and the goal would be that you would try to sort of choreograph things so that all of the different paths leading to a wrong answer, would be out of phase. Some would have positive amplitudes, others would have negative amplitudes, and so they would cancel each other out. Whereas the paths leading to a right answer should all have the same sign. They should all reinforce each other. And if you can arrange that, then when you look at the computer, at the end, then you're going to see, a right answer with high probability. Probably, the most dramatic application of a quantum computer, the one that sort of makes the headlines, is that it could break, almost all of the cryptography that we use to protect our credit card numbers today. Okay, but, that's actually not probably the most useful application, right? As I said, maybe it's useful if you're the first to do it and you don't tell anyone else about it, okay? But, it'll mean that the world will have to switch to other cryptographic codes when this, starts to become practical. Maybe, a much more useful application is one that's, actually the first one that the physicists thought of back in the 1980s, and one that's so obvious that we barely even talk about it. Namely, you can use a quantum computer to simulate quantum physics. For example, if you're designing pharmaceuticals, if you're trying to design new nanomaterials, if you're trying to understand high-temperature superconductors or do high-energy physics, do quantum chemistry, right, or biochemistry. Okay, for any of these applications, any place where sort of understanding the quantum, behavior of atoms and molecules is relevant, well, a quantum computer sort of naturally implements those dynamics, and so, it could give you huge speed-ups in simulating those sorts of things. And then probably the third application of quantum computers is that you can try to throw them at these NP-complete problems, like combinatorial optimization problems, like airline scheduling, or like the traveling salesman problem, or any problem where you have a whole bunch of constraints that you're trying to satisfy, right? And this is a huge, huge class of practical problems that people try to solve. But now for these problems, we don't yet know sort of how much of an advantage quantum computers are actually going to give you. If there's some fundamental reason why you can't build a quantum computer, then I hope that we discover that, because that would be 100 times more exciting than success in building one. An in principle, impossibility of building quantum computers, right, would force us to revise our whole conception of the laws of physics.